Have you ever been streaming a movie during a thunderstorm and wondered, how is this even working? How does it not just dissolve into a mess of pixels? Well, the answer is this incredible, invisible shield that's constantly protecting our digital world.
I mean, really think about it. We are blasting data through the air, across oceans, bouncing it off satellites in space. It's a chaotic journey. So how does any of it arrive in one piece? This question gets right to the heart of some invisible magic that's literally holding our modern lives together.
All right, so to understand the solution, we first have to appreciate just how massive the problem is. You see, every single piece of digital info we send out is constantly getting attacked by noise, interference, all sorts of things trying to corrupt it.
Imagine your data starts out as this perfect, clean sequence of ones and zeros, right? But the second it goes out into the real world, bam, it gets messy. It's like you wrote a perfect message, put it in a bottle, and tossed it into a stormy sea. By the time it washes up on shore, some of the letters are smudged, others are just gone completely. Your perfect signal is now a jumbled mess.
So how do we possibly fight back against this digital storm? Well, we use this brilliant thing called channel coding. It's basically a way of adding a little bit of smart extra information to our original message. Think of it like building an invisible force field around our data to protect it from all that chaos.
So how do we start building this shield? Well, the most obvious idea is usually the simplest one, right? If you're in a noisy room and you really want someone to hear you, what do? You just say it again, and maybe one more time for good measure.
And that's exactly what repetition coding is. It's as simple as it sounds. So instead of sending the number 1 just once, we send it 3 times, 1, 1, 1. Now, even if the noisy channel messes one of those bits up, say the receiver gets 101, it's no big deal. The receiver just takes a quick vote. It sees 2 ones and 1 0. The ones win. It can be pretty confident the original message was a 1. Easy, right?
Well, yeah, but there is a huge catch. While this totally works, it is incredibly inefficient. Think about it. We had to send 3 bits of data just to get 1 bit of information across. That just slashed our speed down to a third of what it could be. So yeah, we made the message safer, but we also made it painfully slow.
Okay, so simple repetition just isn't going to cut it. We need something that's both tough and fast. We need to get smarter. And that brings us to the really elegant solution, something called linear block codes. Now, the idea here is pure genius. Instead of repeating the entire message, we just add a few carefully designed extra bits. We call these parity bits. They act like a secret key or a little checksum. For example, a single parity bit could just tell the receiver if the original message had an even or odd number of ones. If the message shows up and that parity check doesn't add up, the receiver knows, whoa, something went wrong here. It's a way to check for errors and even fix them without sending 3 full copies.
So what's the magic that makes these smart codes work? It really all comes down to a cool concept called Hamming distance. It's just a way of measuring how different 2 code words are. All you do is line them up and count how many of the bits don't match. The bigger that distance, the better your code is.
And this slide just lays it out perfectly. On the left, you've got code words with a low Hamming distance. A single bit flip is all it takes to accidentally turn one code word into another. Total confusion. But on the right, our code words 000 and 111 have a high Hamming distance. They are so different, so far apart, that even if a bit gets flipped, the corrupted message is still way closer to the right answer than any other possibility.
Okay, but what happens when that stormy sea doesn't just splash our message, but sends a giant wave crashing over it? I'm talking about a burst of errors that wipes out a whole chunk of data all at once. This is a massive problem, especially for things like your cell phone.
These burst errors can totally overwhelm codes that are just designed to fix 1 or 2 random mistakes. A single burst can damage so many bits in a row that the receiver has absolutely no chance of figuring out what was originally sent. It's like losing an entire word out of a sentence. The whole thing stops making sense.
So to fight this, engineers came up with this brilliant, almost counterintuitive trick called interleaving. You know what it is? It's basically shuffling your data on purpose, like a deck of cards, before you even send it.
And this slide shows you the magic trick in action. See the data in its original order at the top? Then we interleave it. We shuffle it all up. Now that nasty burst of errors still hits and corrupts a bunch of bits in a row. But, and here's the clever part, when the receiver gets the message and unshuffles it back to its original order, that one devastating burst has been broken up and spread out into a few small, scattered, and now easily fixable errors. It's just an incredibly smart way to spread out the damage so it's not fatal. Okay, so the big takeaway here is that when you're designing a real-world communications system, doesn't matter if it's for your smartphone or a Mars rover, it's not about finding one single perfect code. It's really all about making smart compromises. It's a balancing act.
Now, don't worry about all the different boxes in this diagram. The main thing to see is that our channel coding block is just one piece of a much bigger puzzle. And the choices an engineer makes right there have a huge ripple effect on everything else in the system, from how long the battery lasts to how fast you can download a file.
This chart here is basically the engineer's map. It shows the fundamental trade-offs they're always wrestling with. You've got speed, power, and errors. The thing is, you can't have the best of all three at once. You always have to decide what's most important for the thing you're building.
So how do you make those choices? Well, it's this constant balancing act. You want fewer errors? Okay, you can shout louder by cranking up the power, but that's going to kill your battery. Or you can speak slower by lowering your data rate. Another option is to use a more powerful, more complex code, but that needs a beefier processor to run it. It always comes down to a trade-off between power, speed, and complexity. You just can't have everything.
And this brings us to a really crucial point. For a long time, the main solution to noise was just to be louder. Just blast the signal with more power. But as this quote points out, our computer chips have gotten so fast and so powerful that it's now way more efficient to just use cleverer coding. Smart algorithms are finally beating brute force. And that right there is a total game changer.
So the next time you're streaming a movie, or using GPS, or even just talking on your phone, take a second to think about this invisible shield. From your Wi-Fi at home to probes in deep space, these ideas are working non-stop, silently fixing mistakes and holding our digital world together. So you have to wonder, what other invisible systems are making all this possible? And what would happen if they ever stopped working?